Hi students, welcome to my YouTube channel SADHIK Physics, where you can learn physics very easily. Right? If you are the first time, if you are seeing, please go through my past videos, know how easily I taught all different topics. So today's topic now we'll discuss from the ray optics, that is refraction and up to the total internal reflection now, and we'll go for different applications now, and different model questions also we will discuss in this video now, right? So if you are first time, please subscribe to my channel now. Clear? So today we'll discuss refraction now. Let us come to the topic, that is refraction. So refraction of light. We know that where you will see this refraction now, right? Mostly if you go to some shops, no, therefore in that near to the shop, no, they will place some glass tumbler, so transparent glass, in that they will fill the water, they will place a lemon, right? So if you see from outside, no, that lemon looks like very bigger onto this one now, right? Why it looks bigger, right? And also if you place any one paper below the some glass plate, no, it looks like it appears to be raised onto this. And also if you observe the swimming pool, no, therefore the base of the swimming pool looks like slightly raised. You understand, no? So this all because of due to the refraction. Here I told glass, water, air, so these all are the certain mediums, different transparent mediums now. We know the speed of the light. So speed of the light in one medium and another medium, like a transparent medium. So the speed of the light, it will be the different. So where the speed of the light is maximum, so that type of medium we will call it as like a rarer medium. So where speed of the light is maximum, we can take it as like a air, vacuum. So there the speed of the light is maximum now. Where the speed of the light is minimum, so that we can call it as like a optically denser medium. Optically denser, where the speed of the light is slightly lower now. Therefore, so that medium we will call it as like a optically denser medium. So like you know that where the speed of the light is minimum, you can take it as like a glass, water, diamond. So you can understand that denser medium means, so that means it is more denser. This is your air, vacuum. So vacuum, therefore rarer medium and denser medium. You will think that it is like a density of the air is lesser than density of the glass, no? So but obviously it is true, but it is not that density difference here, no. So optically denser medium means where the speed of the light is minimum. So that type of medium we will call it as like a optically denser medium, not related to the density of that substance onto this one. Clear? Some turpentile is there, no, where density of that substance is lesser, but speed of the light, it will be the different onto this, right? So it is not related to the mass density, it is related to the optical density. Clear? Now the speed of the light is lesser. Now this is a medium is there. Now if a light ray is travelling from one medium to another medium, suppose light ray is travelling from where air or vacuum to, so therefore this is, we can call it as like a incident ray, and entering into the other medium now. When it is entering into the other medium, speed is different now. So due to the change in the speed, it will if it is entering from rarer to denser, it is always bend toward the normal. So this is your angle of refraction, and this is your angle of incidence. This is nothing but a normal. When a light ray is travelling from rarer medium to denser medium, always a refracted ray will bend toward the normal onto this. Suppose if a light ray is travelling from denser medium to rarer medium, no, suppose here it is this is your denser medium, this is your rarer medium. If a light ray is travelling from denser medium to therefore here at rarer medium, no, this is your incident ray, so this is your angle of incidence, so denser medium, and this is rarer medium. Therefore, if a light ray is entering into the rarer medium, speed of the light, it will be increases. When speed of the light is increased, so therefore it will bend away from the normal now. You understand, no? So this type of bending of a light ray when it is traveling from one medium to another medium, we will call it as like a refraction. Why this takes place? No, because of due to the change in the speed of light. Clear? So that means you can remember these 2 points only most important. No, if a light ray is traveling from rarer medium to denser medium, it is always bend toward the normal. If a light ray is traveling from denser medium to rarer medium, it will bend away from the normal. That's all. Here, when light ray is traveling from rarer to denser, angle of incidence is greater than angle of refraction. No? Here, when light ray is traveling from denser to rarer, angle of incidence is smaller than angle of refraction. Now, what will be the angle of deviation now? Therefore, here light ray should go toward this side. This is your incident ray, but how much is bending now? This much amount of deviation is taken place. No, this is called angle of deviation. This angle of deviation can be written as like a total I. So therefore, I minus R. So this we can call it as like a angle of deviation. Here light ray, therefore this is gone like this. No, this much amount of is getting deviated. No, so angle of deviation can be written as R minus I. Clear? So this is your angle of deviation. No, so this is your about refraction. So one important thing is, therefore light ray traveling from rarer to denser bend toward the normal, light ray traveling from denser to rarer bend away from the normal. Due to this only, so the refraction, this phenomenon only we can call it as like a refraction. And one application, no, you can think that, so here suppose if a light ray is, this is your rarer medium and this is your denser medium. Suppose if a light ray is along the normal, that means this you can call it as incident ray is along normal. We will call it as normal incidence. Normal incidence. Clear? So therefore this is your normal, this is your angle of incidence. No, so therefore it will not undergo any refraction here. No, so therefore here angle of incidence is 0, angle of refraction is 0, angle of deviation is also 0. Normal incidence means is incident perpendicular to the boundary between the two media. Clear? So this we can call it as like a normal incidence. Now we will go for loss of refraction. Now what is loss of refraction now? Very important. No, before going to this loss of refraction, no, we should understand one important term, that is called refractive index. Refractive index, very important. No, first let us go for absolute refractive index and another one is relative refractive index. First of all, basic thing is refractive index. What is meant by this refractive index? So this concept, no, most of the students know, they will confuse. So try to listen carefully onto this one, no, so that you will not get any confusion on this one. Refractive index is defined as refractive index of any substance. So how to represent it now? Therefore, here refractive index of the glass with respect to air. So anything we are comparing with air, that is called absolute refractive index. What is this? Absolute refractive index. Therefore, what you are telling now? Refractive index of the glass with respect to the air. So how to rewrite it now? Therefore, here air is there, no? We are comparing air or vacuum, no? So therefore, speed of the light in air, so by speed of the light in glass. So this ratio we will call it as like a refractive index. If we are comparing with air, that is called absolute refractive index now. So speed of the light in air by speed of the light in glass. And also one important point, refractive index in this refraction, no. So you know the speed of the light, no, that is nothing but a wavelength into frequency. Clear? In refraction, what it will change now? Speed of the light will change Speed of the light will change and wavelength will change, but frequency do not change. Frequency do not change in the refraction. In refraction, not refractive index, no. In refraction, no. So what is going to change now? Only the speed of the light it will change and wavelength will change in refraction. Wavelength will change and wavelength and speed only it will change now, but frequency do not change onto this. Therefore, what we can rewrite it here now, therefore, here speed wavelength into frequency, wavelength in air into frequency by wavelength in the glass, so into frequency, frequency cancel, therefore you can rewrite it as like this, wavelength in glass by wavelength in wavelength in air by wavelength in glass. Clear? So this is your absolute refractive index. Suppose you can rewrite it as refractive index of the water with respect to air. So that means C by velocity of the light in the water. That is nothing but a wavelength of the light in air by wavelength of light in water. These are the absolute values, no. So for the glass, you can take it as this value is nothing but a 3 by 2. For water, refractive index is nothing but a 4 by 3. This is for glass, this is for water. Sometimes if they do not give, therefore you have to use these values. Clear? Absolute refractive index now. Clear? And one more important point now, here you can understand, that is here refractive index is inversely proportional to the speed. That means where the speed of the light is lesser, there refractive index is more. That means which one will reduce the speed of the light, no? So that refractive index, if which one will reduce the speed of the light will be more, so that refractive index will be greater. That means it is inversely proportional now. And also it is inversely proportional to the wavelength. Therefore, so here refractive index is inversely proportional to the wavelength, inversely proportional to the speed of the light. That means, you know, wavelength of your blue color will be smaller than wavelength of your red color. Clear? So red color wavelength is larger. So it is inversely proportional. Refractive index of the blue is greater than refractive index of your red. Clear? Refractive index of the blue color light, so will be greater than refractive index of your red color. And this refractive index does not have any units, no? No units. Understand? No? Therefore, no dimensions. No units, no dimensions onto this. Clear? Clear? It is inversely proportional to the speed and it is inversely proportional to the wavelength. Clear? This is absolute refractive index, means what? We are comparing with a air or vacuum. So therefore now we can have relative refractive index. Relative refractive index. What is this relative refractive index now? Relative means we are comparing with one medium with another medium now. That means, so what you can write it now? Refractive index of the glass with respect to the water. So what you can write it now? How I read this one now? Refractive index of the glass with respect to the water. Clear? That means refractive index of the glass with respect to air means speed of the light in air by speed of the light in glass. Like that only. So refractive index of the glass with respect to the water is nothing but a, so therefore speed of the light in water by speed of the light in glass. That is nothing but a, so wavelength in water by wavelength in the glass. This is called, and one more formula is also is there, no? We will write on specially onto this, right? So in this way. Clear? So we can rewrite it as refractive index of the glass with respect to the water. What we written now? Speed of the light in water by speed of the light in glass. I can multiply with C and C. Multiply and divide with C. So cancel speed of the light now. So I can rewrite it as, so what I can write it now? So C by, therefore Vg by C by Vw. Clear? So you can rewrite it as, therefore Vw by Vg, you will get it. Clear? So C, speed of the light by glass, means absolute refractive index of the glass by absolute refractive index of the water. Clear? That means what I can rewrite it now? So here I can rewrite it as, this is relative refractive index. How I read no? Refractive index of the glass with respect to the water means here refractive index of the glass now. Therefore, that is absolute refractive index of the glass by absolute refractive index of the water. Clear? In this way, so you can compare from one media to another media. Clear? So now just let us test this one now. So here now refractive index of the glass with respect, okay, we will write down 2 and 1, okay, right, we will write it glass with respect to the water into refractive index of the water with respect to the glass. What you can rewrite it now? What you can get it now here? So therefore here refractive index, therefore here we can write down absolute refractive index of the glass by absolute refractive index of the water into here. So therefore absolute refractive index of the water by therefore glass. Just now we written no, this you can cancel it no, this you can cancel, you will get it is equal to 1. That means here refractive index of the glass with respect to the water can be written as 1 by refractive index of the water with respect to the glass. So this confusion no, so it will be there most of the students no, so they will confuse this. So please listen carefully so that you can understand very clearly about this concept. So like this you can solve one question no. Suppose here refractive index of 2, 1, refractive index of 3, 4, refractive index of 4, 1. Therefore here it will be, okay, so therefore here it will be the 2. Clear? So this all are, you can rewrite it as, what you can write it now, this formula. So you can get it as, so here this here, okay, this is refractive index second by 1 into refractive index of third by 4 into refractive index of 4 by 2. These two get cancelled, refractive index 3 by refractive index of 1, that implies refractive index of 1 with respect to 3 with respect to 1, refractive index of 3 with respect to 1. This it will be your answer on this. Clear? So this is about basic things no, related to the refractive index now. Clear? So we will see some questions also. Therefore now we will go for one concept now, that is laws of refraction. What are the laws of refraction now? Suppose here how the refraction will take place now? Here light ray is incident here now, clear, and it will bend toward this side. So therefore rarer medium and denser medium now. So therefore here I and this is R. So this is your normal, this is your incident ray, refracted ray. What are the laws of refraction now? Right? So you might know this one no? Therefore you know incident ray and refracted ray and normal all lies in same plane. You might have know this one no? Therefore they all are lying in the same plane. Next very important now, that is Snell's law. Total, I am telling you, total ray optics is based on this Snell's law. So what is this Snell's law now? Therefore here you can rewrite it as, so here is there no, therefore you try to draw one circle of radius of this one, radius of common radius no, then if you draw one circle like this. So therefore here there will be a perpendicular distance is there no, this perpendicular distance, this ratio is always equal to the refractive index. So we are not going to derive onto this, but how to use it I will tell you, very important one now. Without Snell's law you cannot able to complete the ray optics now. Clear? So now what is this Snell's law? How to write it? Very simple one now. Suppose here it is rarer medium, this is your rarer medium and your denser medium. Refractive index, absolute refractive index. So therefore here now how to write it now? How to write the Snell's law now? So you need to travel along the light ray. That means light ray is traveling like this. In which medium? Rarer medium. So refractive index of the rarer medium into what is making the angle now? Therefore sin I. And entering into which medium? Denser medium. Refractive index of the denser medium into what is that making angle now? Therefore sin R. You understand? No? So this is your Snell's law. Clear? Snell's law. Therefore, so rarer medium absolute refractive index only always. Therefore, NR into sin I is equals to ND into sin R. So suppose this is air or vacuum is there, air or vacuum, no? So refractive index of the air or vacuum, it is always equal to 1 because speed of the light by speed of the light in air and air no cancel onto this, right? So what you can write it now? 1 into sin I is equals to n into sin R. So therefore n is equals to sin I by therefore sin R. Most of the times no, you might have listened this, you might have seen this formula. I don't suggest to use this one now, I suggest always use this. What is this one now? You have to travel along the light ray, therefore light ray is traveling along the rarer medium, refractive index, absolute refractive index of that medium. Entering into this one now, so absolute refractive index into sin R. So NR into sin I is equals to ND into sin R, that's all. So total ray optics was designed based on this formula. Clear? So that much is important is this Snell's law. Clear? Right? So thoroughly practice onto this. You can solve the any type of problem no by using this one. All even lens maker formula is also based on this concept only, right? So be careful on this one. Clear? We'll do some questions onto this one no based on this. So very detailedly now. Now we'll apply, right? So this Snell's law. So we are going to apply for different scenarios now. Clear? So suppose here, therefore, suppose this is your water now, right? This is water, right? Now suppose here there is an object is there now. This is one object, right? So what is there now? This is your, we can call it as like a real depth of this one. Now this light rays, what will happen now? From this object, light rays will go like this. Clear? So light rays will go and it is traveling from denser medium to rarer medium. So therefore this is making an angle of incidence is I. So when it is traveling from denser medium to rarer medium, what will happen now? It will bend away from the normal. So it will go like this. If these light rays are coming and falling on your eyes now, so what you feel now? You feel that these light rays are coming from here. So therefore objects looks like here. That means what is happening now? From here to here is getting shifted onto this one now. So this we can call it as like a apparent depth, and this one we can call it as like a shift. That's why the floor of a swimming pool now looks like it is like a slightly raised onto this. Clear? So why this takes place now? Because of due to this refraction onto this one, right? So we can write it as like a shift. How you can write down the shift now? Shift is nothing but a total real depth minus apparent depth. Apparent means how much we are going to look at. Real depth means really how much depth it is there now. So what will be the refractive index of this one now? Therefore refractive index we can rewrite it as refractive index of the denser medium with respect to the rarer medium. If this is air or vacuum now, therefore it is 1 absolute refractive index. We can rewrite it as like a real depth by apparent depth. Clear? Real depth by apparent depth. So therefore you can rewrite it as, so apparent depth is equals can be written as real depth by n. So therefore your shift can be written as real depth minus apparent depth can be written as like a real depth by it is n. So you can write down real depth, therefore 1 minus 1 by n. Suppose this real depth is h, no. So shift is equals to can be written as h into 1 minus 1 by n will be the shift. It looks like this much amount of is going to raised. Clear? So therefore it is h into 1 minus 1 by n. Clear? So this is very important concept. Clear? So here object is there in the denser medium, no? So but we are viewing from the rarer medium. So that means we are standing outside and we are seeing the which object is there inside the water. Suppose we can go for one more thing, no? Therefore here suppose this is the water is there now. This is one water. So therefore here there is a fish is there now. This is one fish. Right. So this is the fish is there now, or fisherman is there now. So this fish now. So for this fish. So now suppose any one person is there, or one person is there here very near to this. Therefore suppose a light rays from this person, no? So light rays from this person is coming here now. Light rays from this person is coming to here. So therefore light rays are traveling from rarer medium to denser medium. This light rays what will happen now? This light rays it will be bent toward the normal. So therefore this it will be your refracted ray. This light rays appears to be coming from here. So therefore for this fish no, so this person looks like very big taller person here now. You understand no? So that's why this fish no, it will not stay very at one place, no, it will run away onto this by seeing. Why? Because it looks like very big person is coming very near to this. So really this is your a real height. Therefore this we can call it as like a apparent height. You understand no? So what will be the refractive index of this one now? Refractive index of this denser with respect to rarer can write it as like a apparent height by, therefore we can call it as like a real height. And what is the shift here now? This much amount of shift is taken place now. Shift can be written as like a apparent height minus a real height. So this apparent height can be written as like a real height into refractive index, no? So why? Because always why you are calculating apparent height, no? Apparent means we cannot calculate it. Real height means how much depth is there, we can calculate easily, but how much apparent height is there, no, we cannot able to calculate it now. That's why we are trying to eliminate it, no? Apparent height it will be equal to, this is your apparent height, it will be equal to refractive index into real height. So therefore here real height, therefore n minus 1 into real height of this one. No? Suppose height of the person is h, no? So this is your h. This is, we can call it as like a shift of this person on this. Clear? You understand? No? Right? So in this way, therefore this person it is looks like a very bigger for to this fish. So you try this concept, no? Therefore if you are swimming inside the water, if you are seeing right from the water, you try to see outside the tree or some other thing, no? Therefore it looks like very bigger onto this. Why? Is because of due to this refraction on this. Clear? Right? We'll see one concept now. Suppose here different liquids are there now. Suppose here there is a one liquid is there, no, which is we cannot able to mix it onto this. This is your H1 having refractive index is N1, and another one more liquid we are going to take it now. Therefore here, so this is your height H2 and refractive index is N2. So again one more thing, no, you can take it here, no. Therefore here, so this is your H3 and N3, like this. Some other objects are there now. Now what will happen now? Suppose here there is a three different substances are there. So here we are going to keep it one object here now. This is one object. Now what will be the shift it is going to take place onto this. So, how to draw the ray diagrams also very very important. No? So, this light ray, so it is going onto this one, no? This light ray. So, it is going, suppose if the refractive index of second one is greater, suppose n2 is greater than n1, what will happen now? It is entering from rarer to denser onto this one, no? It will bend toward the normal. Clear? So, bend toward the normal here now, like this. Suppose n3 is smaller than n2, that means this is smaller onto this one, no? It is entering from denser to rarer, it will bend away from the normal, like this. So, suppose this is your air onto this. Clear? Now, what happens now? Here it will still bend away from this one, no? So, therefore, here this light ray is coming and falling on your eyes, no? So, what will happen now? This light rays appears to be coming from here. This is called apparent depth. This we can call it as like a real depth onto this. Clear? So, we written that we written the shift for each and every slab onto this one, no? Total shift, what you can write it now? Total shift or total refractive index. Now, what is the refractive index here now? Real depth. What is the real depth now? Real depth here now, because we are seeing from outside. Real depth is nothing but a h1 plus h2 plus h3, so on onto this. Clear? What will be the apparent depth now? You know that due to this one now, therefore refractive index is nothing but a, so real depth by apparent, so depth onto this. Clear? So, this apparent depth you can write it as apparent depth can be written as, so h1 by n1. Clear? So, due to this one now, due to this one now, due to this one now, we can rewrite it as apparent depth is nothing but a h1 by n1 plus h2 by n2 plus h3 by n3, so on. All are absolute refractive index. In this way, you can calculate the combined refractive index of this combination onto this. Clear? So, right, you can see any different combinations, no? If all are equal, right, different things, no? You can calculate it. So, this is slightly important concept onto this. Clear? So, different class slabs we are going to keep it now. How to draw the ray diagrams based on the refractive index also we learnt here now. Clear? Right? Always remember that if it is entering into more denser medium, bend toward the normal. If it is entering into rarer medium, bend away from the normal. That's all. Only these things, no, you remember, then you can solve any type of questions on this. Clear? So, this is like some simple question on this. Clear? So, we will go for refraction through the glass slab. Refraction through the glass slab. Suppose there is one glass slab is there, no? So, here there is one glass slab. Okay. So, now what happens now? Now, suppose there is an incident ray is there now. This is your incident ray. This we can rewrite it as angle of incidence. This is here having the thickness is T and having the refractive index. This is air is there, no? And also it is air is there. Clear? Right? So, now what happens now? It is entering from rarer medium to denser medium. What it will do now? It will bend toward the normal. It will go like this. Clear? So, this is your angle of refraction now. So, also while remember that if it is traveling in one medium, it will travel in the straight line only, right? So, like a ray. So, here therefore, this also it will be like a R, and entering from denser medium to rarer medium, bend away from the normal like this. This is your angle of emergence now. You try to observe this one now. Therefore, this light ray, so which is coming out onto this one now. So, whatever this light ray which is coming out, so this light ray it will be compulsory, this is your emergent ray. So, this light ray emergent ray which is entering into the same medium, therefore, this incident ray and emergent ray both are parallel, right. So, therefore if possible no, I'll show here no. So therefore there is a one ray diagram no, you can see it no, some small experiment how they are doing onto this, you can see it here, clear. So that means this is your, so right, so emergent ray and incident ray both are parallel onto this, clear. So this displacement which is there no, this we can call it as like a lateral displacement. So that means how much it is getting displaced onto this, laterally getting displaced onto this, clear. This lateral displacement no, we want to calculate it no here. So this d we want to calculate it no. How to do it now? So this we can, this angle we can call it as like a angle of deviation, that is nothing but I minus r. So you can draw the triangle here no. This is your refracted ray. So this one no, this is your incident ray. This is your angle of deviation no, that is nothing but a I minus r. This is your d. So this is your suppose x. What you can write it now? This is your opposite side. This is your hypotenuse. This is perpendicular onto this one no, perpendicular no. So what you can write it now? Sine of I minus r. Right. So opposite side d by therefore here x. Therefore d is equals to x into sine of I minus r. Now x, what is this x now? This how much amount of distance travelled by the light in the glass, this is your x, clear. So to calculate this one now, one more thing we can use it here. So what are they now? Here this normal I will take it to here directly. So therefore this is your perpendicular, this triangle now. Therefore this triangle I can take it. This length is t. So therefore here this is your r, clear. So therefore here we want to write it as this is your x. So what you can write it now? Adjacent side by hypotenuse. Therefore cos r is equals to x by t. So therefore x is equals to, sorry, t by x. Adjacent side by t by x, that implies x is equals to t by cos r. So what you can rewrite it now? D is equals to, x value is nothing but a t by cos r into sine of I minus r. This is your lateral displacement, how much amount of getting displaced, clear. So therefore how much amount of time taken to travel this one now? Therefore, so the time taken to travel this, how much distance it is traveling now? So this x distance it is traveling here no, x distance, because how much amount of time taken to come out onto this, time taken by the light ray to emerge out, right. So time is nothing but what, so therefore, so speed of the light in glass, clear. Speed of the light in glass is nothing but a distance by, therefore time taken onto this one no, time, this is your time, clear. So therefore here this time it will be equal to time taken by emitting the light ray, I mean time taken the light ray to cross this one. So x value is how much now? Therefore it will be t by therefore cos r into velocity of the light in that medium. So what will be the velocity of the light in this medium now? You know that speed of the light it will be equal to speed of the light in air, I mean refractive index is equals to speed of the light in air by speed of the light in medium. So v is equals to c by n. So we can rewrite it as time it will be equal to t by cos r into speed is equals to into speed of the light into n. So this is your n is nothing but a refractive index of this with respect to the air, absolute refractive index, clear. So this is the time taken by the light ray to cross this slab, and this much amount of angular, I mean lateral displacement is taken place no in this glass slab, right. So this is nothing but a refraction through the glass slab. So I will show the experiment in this one no, right. So go through it onto this, clear. Now we will discuss one more concept no, right. So next one we will go for optical path length. Therefore suppose this is your one glass or anything no, suppose here how much amount of time taken. This is your length of this one, now it is L. So therefore speed of the light which is entering here, no, therefore light is entering, how much amount of time taken to come out onto this. This is the time we want to calculate it now. So just now we discussed, no, so how much amount of, therefore in this one, no, so we need to calculate what will be the speed of the light inside this one now. You know refractive index of this, so of this glass with respect to the air is nothing but a speed of the light in the air by the speed of the light in the glass slab, or V is equals to C by N. V is equals to what, again distance by time, no, therefore length by time onto this one, no, therefore time is equals to N into L by C. So this N into L, therefore how much actual distance it is travelling, no, N into L, that is the path which is followed onto this. This N into L we can call it as like a optical path length. By speed of the light in air or vacuum. So optical path length we can rewrite it as optical path length can be written as, so refractive index into the thickness of that. Clear? So the distance of that. Clear? In this way you can calculate the time taken to cross this glass slab, right? So different right, refractive index is inversely proportional to the wavelength onto this sun, no. So that means your time is directly proportional to the refractive index, no. So refractive index is inversely proportional to the wavelength, no. So suppose if you are sending the different colored light rays onto this sun, no, so that means time it will be equal to, therefore time it will be equal to, so time is directly proportional to the N and it is inversely proportional to the wavelength. That means, so wavelength of your red color is greater than wavelength of your blue color. So therefore time taken by the red color is smaller than time taken by the blue color. So that means, so if you send blue color and red color onto this one, no, therefore so time taken by the red color is smaller onto this one, therefore red color light will come out faster onto this one, no, red, I mean compared to the blue color light onto this. Clear? You understand, no? So in this way, so you need to remember this concept onto this. Clear? You understand, no? Right. Now let us go for one more concept, no, that is nothing but a total internal reflection, right? So total internal reflection, very important concept, no, very important, critical angle and total internal reflection. So suppose if a light ray, so here this is your medium onto this, or this is some water onto this, no, or any other medium onto this. Clear? This is called optically denser medium, no. Now suppose there is a light rays are coming onto this. These are the light rays which are coming onto this. Some one light ray will go and fall onto this one, no? Therefore it is traveling from denser to rarer. Clear? So this is your angle of incidence, no? Therefore it will be coming out, entering into the rarer medium. What it will do now? It will bend away from the normal. Angle of refraction is greater than your angle of incidence. Now you try to observe, if the angle of incidence is increases, angle of refraction is also increases onto this. Clear? So therefore at certain angle of incidence, no, so what will happen now? At certain angle of incidence, the refracted ray will retrace the boundary between the two media, or it will angle of refraction makes like a 90 degree. Clear? Or it is going to retrace the boundary between the rarer medium and denser medium now. So this angle of incidence will call it as like a critical angle. This angle will call it as critical angle. Now, so one more important concept, no. Suppose here, if a light ray, so if a light ray is incident, more than angle of incidence, critical angle now. Angle of incidence is greater than the critical angle. So that means it is more than this one, no. What will happen now? Definitely it is going to rebound back into the same medium. So that means it is right, it is undergoing like a reflection now. It is looking like a reflection. So this phenomenon we will call it as like a total internal reflection. Clear? So total internal reflection to takes place. Now what are the conditions is required? Now compulsory. What are the conditions? First condition, light ray should travel from denser medium to rarer medium. You understand? No? It has to travel from denser medium to rarer medium. Second one, angle of incidence should always greater than, so critical angle onto this. Then only the total internal reflection will take place. Total internal reflection conditions are what? Light ray should travel from denser medium to rarer medium, and angle of incidence should be greater than critical angle. If it is equal to the critical angle, it will retrace the path. Therefore, for calculation purpose, therefore we always use critical angle as your base onto this. Clear? So these are the two conditions you have to follow. Clear? So here we can apply for the critical angle, Snell's law you can apply. Light ray is travelling from denser medium. So therefore here light ray is travelling like this, we will apply the Snell's law here. How to apply Snell's law? Refractive index of the denser medium into what is this angle sin C, and entering into the rarer medium, refractive index of the rarer medium. What is the angle making See here light rays coming and going. Therefore sin 90. Sin 90 is 1. So therefore sin C is equals to refractive index of the rarer medium by refractive index of the denser medium. Clear? So if rarer medium is air or vacuum, this is your air or vacuum. So therefore sin C is equals to 1 by n. Clear? 1 by n. So now you try to observe, critical angle is inversely proportional to the refractive index. Refractive index is inversely proportional to the speed. Refractive index is inversely proportional to the wavelength. So now critical angle is, it is inversely proportional to the refractive index. Critical angle is directly proportional to the speed, and critical angle is directly proportional to the wavelength. So that means what you can write it now? Here suppose wavelength of your red color is greater than wavelength of your blue color. This is you already know it. So therefore critical angle for red color will be greater than critical angle for blue color. Clear? Critical angle for blue color. Understand? So in this way you can calculate the critical angle onto this. Clear? Now we will see some applications on this one. Suppose some concept here. Suppose here there is one medium is there. So here there is a water is there. Here there is one bulb is there. Here there is a bulb is there here. Here there is a bulb is there. So light rays are coming and going from denser medium to rarer medium. So therefore some light rays so it will come out onto this, but some light rays which is coming here so which are falling here, so at an angle of critical angle it will retrace its path onto this. Retrace its path. Clear? Critical angle. So through this one the light will be coming out onto this. The light it will be coming out onto this. Through this one light it will be coming out. Clear? So but here beyond this one light will not be coming out onto this, or if it is more than this one undergo like a total internal reflection. That means if a bulb is kept under the water onto this one, only certain amount of portion of the light it will be coming out onto this. So we want to calculate how much amount of area, so where light it will be comes out on from this one, we want to calculate it now. Clear? So how to calculate it now? So very simple one. Suppose this bulb is kept at certain depth, therefore it is h. This is critical angle, means this is also critical angle. This total we can call it as like a apex angle. Apex angle where light it will be emitted is nothing but a 2c. This c and c. Clear? Is like the cone of light it will be coming out onto this. Clear? Now what you can write it now? We want to write it as like this is your radius of this one. We want to calculate it. So tan c can be written as, so tan c, this is a triangle, so r by h, opposite side by adjacent side. So R is equals to H into tan C. So this is your radius. So where this light is emerging onto this area, what you can write it now, pi R square, therefore pi into H square into tan square into C. Clear? So this much amount of area. But we don't know critical angle, we know refractive index only. Therefore, how to write this formula in terms of refractive index? Let us see here now. You know, sin C can be written as 1 by n. Clear? So you know sin value is nothing but what? Opposite side by hypotenuse. Clear? Hypotenuse, no? Therefore we can draw the triangle here now. So therefore here this is C, opposite side value is how much now? 1, hypotenuse value is n, adjacent side value is root of n square minus 1. Yes, sir? By using Pythagoras theorem now. So therefore what you can write it now? Tan C, opposite side by adjacent side, root of n square minus 1. So substitute here now, what you will get it now? Pi into h square. So tan square means 1 by, therefore by n square minus 1. This much amount of area where the light it will be comes out onto this. Or we want to stop this no, this much amount of area of the plate, like one plate no, we have to place it so that light will not be coming out on from this one. Clear? This is one of the application of our total internal reflection. Now there are so many applications are there where you will see the total internal reflection, no? So some applications, no, you can go through it, no? What are the applications, no? Total internal reflection, where it will take place, no? Formation of mirages, right? Mirages, no? What is this mirages here now? So you might have see in the summer season, no? Suppose if you are traveling on the road, so if you in the summer season, no? Therefore if you see far away from the on the road, no, you will see that some like a oil is floating onto that. Oh, oil is floating, that means if you go near to that, definitely again oil will disappear, again it will be looking far away onto this. So that is because of due to the mirages only, because of due to total internal reflections now. Clear? So now suppose not only in the summer season, no, if you go in the desert, if you are traveling in the desert now, which is more important? In the deserts you require only the water. Water is more important so than anything onto this. So those who are traveling in the deserts, no, they need of water because of due to dehydration, because of due to the higher temperature on this. So how the mirages will be formed onto this? Listen carefully now. Suppose this is your some sand, it is there, no? This is your sand. Suppose here there is a one small tree is there, no? Small tree is there. Now due to sunlight, no, in the daytime, due to sunlight, so what will happen now? So this sand, what will happen now? Sand will be get heated up quickly, heated up. So therefore what will happen now? Here the sand, it will be very very hot onto this. The air onto this and now the air onto this, so it will be get heated up, no? This, what is the air is there, no? This air it will be slightly raised up, because temperature is increases, kinetic energy of the air molecule will increase, so slightly it is going to raised up now. Therefore here more amount of air, it will be air particles, no, got collected here now. So this it is creating like a partially denser medium, partially denser. Here more air particles are not there, we will call it as like a partially rarer. Clear? Suppose from this one now, due to this denser medium and rarer medium, suppose from this one now light rays are coming now, light rays are coming and falling. So therefore most of the light rays now will get refracted back, no? But some light rays now, what will happen now? Some light rays now, it will be falling at greater than the critical angle onto this one now. That light ray, what it will do now? It will undergo like a total internal reflection. Suppose this person is coming from here now. So this light ray, it will be reaching to his eyes now. Therefore these light rays are appears to be coming from here. So looks that, therefore here the image it will be created at this point onto this. So therefore where you will look this type of images now, mostly near to the ponds no, therefore the water is there, the tree beside this one no, so the reflection of the tree inside the water, it is looks like this. Therefore he will be very thirsty onto this one no, therefore he will think that here a tree is there, so compulsory water is also will be there. So this image is formed because of due to the water, like that he feels it now, he feels. Then he will come forward no, these reflected light rays are not reaching to this height no, this will get disappear onto this. Clear? That is the reason when you are traveling on the road in the summer season or in the sun, right? So in the afternoon time no, you will see that far away more temperature is there no, at that time where far away on the road you will feel that like some oil is floating. This is because of due to the total internal reflection no. So this is for mirages in the deserts onto this, right? In the cold countries no, therefore you will be having the same type of phenomenon no, in cold countries no, we will call it as like a looming. Clear? So suppose there is a cold countries, what will happen now? So air get cooled onto this one no, therefore air particles will be losing its energy onto this one no, therefore it will be falling very near to the surface of this. Clear? Surface of this one no. Now what will happen now? This will create like a partially denser and most air particles are losing this one no, this we can call it as like a partially so rarer onto this. Clear? Suppose if any light rays are, if any like a one ship is there no, suppose there is a ship is coming on the water here no, there is a ship is coming now. Now the light rays coming from the ship no, so what will happen now? It will be okay. So here there is a ship is there no, the light rays coming from this one no, light rays coming from this, so it is trying to fall here now. These light rays, what will happen? It's falling greater than the critical angle no, some light rays no will get reflected back onto this one no. Suppose any person is there here no, these light rays it undergo like a total internal reflection here no, these light rays are appears to be coming from here, so therefore you will see the ship which is coming in the space, in the sky. It looks like that ship no, which is there in the sky, right? So this phenomenon we will call it as like a looming onto this. Clear? So not only this one no, therefore diamonds no, so diamonds what it will do no, it will go into shine. Why the diamonds will shine no? So refractive index is very large. If refractive index is large, critical angle will be small. If the critical angle is small, so therefore a smaller angle of incidence also it will be undergo like a total internal reflection. Therefore the cutting of the diamond is also one very important thing no. So where light ray, so which is incident here no, so because critical angle is smaller no, this light ray will get which is the light ray entered no, it will undergo like a total internal reflection no, continuously it will undergo like a total internal reflection onto this. So this light will get trapped onto this one no, in this only, therefore so this light will not go out onto this. That's why the diamonds no will be able to shine, so because light is getting trapped inside this one. Clear? You understand no? Right. So in medicine also, therefore we will be using like optical fibers. So therefore this is mostly if you go for endoscopy, right? So if you go to the hospital, therefore endoscopy if they do it no, therefore they will send the pipe through the mouth or through the nose no, they will enter, they will see the our stomach or lungs no, how they are working or what is it, no. Therefore, that pipes which are there, no, that pipes which are utilizing, no, that is nothing but a optical fibers, no. So, this is mostly these optical fibers are used in endoscope. Next one, it is used in mostly in the fiber optic communications, no. In the olden days, you might have seen, right, mostly like a there will be a communication like a the telephones was there, no. So, it was connected with one wire from one point to another point, no, very longer distance, no, that wire communication was takes place onto this, right. So, wires means it will be having large resistance, no, and pulses are very less, no. Therefore, it will be lot of loss of information, due to resistance, no. So, the information cannot be transmitted for longer distance onto this. So, and lot of defects are there, jumping of these signals also takes place, no. Connectivity is very difficult, no. Nowadays, the communication was become very faster, even mobiles are there, internet is there, very high speed. So, therefore, takes place is because of due to the optical fibers. Here we are not using the electricity, we are using the light. So, therefore, light will travel with a faster, no, you know it, right, the speed of the light, no. So, that is why the speed of the communications, no, was increased, right. So, fiber optic communications, no. So, general some idea I will give it, no. This it is also work based on this total internal reflection on this one. So, here this is one some empty pipe which is there, no, which is used onto this. So, here this pipe, no, this pipe is made up of like a core, some higher refractive index, no, refractive index of the core. So, now this is 2 and it is upper layer of this, now there is a one cladding is done onto this. This is your cladding material, cladding, refractive index is 1. So, then again upper layers, no, therefore, there is a opaque will be there, right, and mostly protecting layers will be there, lot of things are there. This is a basic idea first of all. This is one core made up of this one, no, having higher refractive index of the core is greater than the cladding onto this, clear. So, now what happens now, suppose if a light ray is incidenting from here, no, so its particular angle of incidence, no, what is that angle of incidence, no, it should be greater than the critical angle, clear. So, therefore, what will happen now, this is your denser medium, no, this is your denser medium, this is your rarer medium. Now, what will happen now, a greater than the critical angle onto this one, no, then this will get reflected back, and like this also is getting reflected back, like that. If a parallel beam of light rays are incidenting onto this one, no, so a parallel beam of light rays is getting reflected back. Even it is in a zigzag way it is there, no, it does not lose this loss of reflection onto this one, no. So, this information can be undergo like a multiple reflections and it go faster and faster onto this, clear. In this way, so here whatever our information is there, suppose you are talking in the phone, so that phone what it will do, no, it will convert into electrical signals, that electrical signals are converted into like a light onto this. So, this light signals is incident at a particular angle, no. So, then it will undergo like a multiple reflections. In reflections there is no loss of energy, right. So, therefore, here a total internal reflection, no loss of energy. So, it will undergo like a multiple reflections and it go faster, no. And also there is no merging of these light rays, no, it will not take place. So, that is why the jumping of calls, no, right, it is not at all taking place nowadays onto this. In olden days, no, it is very difficult, right. So, therefore, in this way we can transfer the information very faster because of due to the optical fibers onto this. Optical fibers will be working based on the total internal reflection here, clear. What should be the, so angle of incidence now, therefore, here angle of incidence can be written as sin I, it will be equal to root of, so n2 square minus n1 square for a optical fibers onto this, clear. So, sin I it will be equal to root of n2 square minus n1 square. Yeah, okay. I think the time, right. So, maybe with this video may be length, I will collect it and I will do like some numerical questions related to this refraction onto this. Clear? So thank you for watching. Please subscribe to my channel and you can learn physics very easily.